Welcome, everyone. Today I'm meeting with Bertrand Rouet-Leduc from Kyoto University, and I'm talking with him about his recent publication in Nature Communications, where he and his co-worker employed a deep learning approach to monitor methane emissions that previously were not able to detect from the remote sensing database. So yeah, my first question would be about the actual problem you want to tackle with your paper. So you're motivated by the fact that we need to cut down methane emissions globally in order to mitigate further climate warming. And likewise, it's just as important to monitor the actual methane emissions. And in your study, you're writing that this is a major challenge. So can you maybe walk us through why it's so difficult to get actual methane emission monitoring?
Thanks for the great question. The motivation, the background behind this study is that methane accounts for 20 to 30% of global warming, depending on the studies. And it actually stays in the atmosphere only about 10 years, unlike CO2 that stays about 100 years. So actually, if we want to have an impact on climate change in our lifetimes, methane is actually a really good target. And that's why there's a lot of research and government commitments and corporate commitments around methane emissions. The problem is that actually it's very hard to measure. Typically, it's done by cameras mounted on cars or planes or drones, but that doesn't scale. So you can't, of course, you can't fly drones at the scale of countries, let alone the world. So there's been a renewed interest in measuring methane from satellites. But here again, there's actually a trade-off. So basically, there's 4 specifications with the multispectral and hyperspectral satellites: the spatial resolution, the temporal resolution, the spectral resolution, and the coverage. So then these 4 specifications, and they can't all be good at the same time. Basically, you have to pick 3 at most. That would be good, and the 4th would be bad. So far, most methane detections have been done using hyperspectral satellites. And so the choice here is that the spectral resolution will be very good. And the trade-off typically is either the spatial resolution, so that's, for example, Sentinel-5, that's used a lot, the troponin instrument, that gives very accurate methane measurements, but at somewhat large scale, so the pixel size is 10 kilometers. Another choice can be done on the coverage. That's often very much the case. So, for example, in the oil and gas industry, uses satellites that have poor coverage but good spatial resolution, good temporal resolution, and a pixel size at about 20 meters that enables to attribute which site is leaking, which site needs repair. And so I should come back to the background again, because so about 30% of methane emissions comes from the oil and gas industry. So that's a critical aspect of methane emissions, is finding which part of the oil and gas infrastructure has methane leaks. And so going back to the satellite, so there's those trade-offs that have to be made. And in our research, we made a completely different choice in terms of this trade-off. In our case, we chose to use multispectral satellites. And so here the spectral resolution is bad, but all the rest is very good. So the pixel size is 20 meters, so small enough to find where the leak is actually coming from. The temporal resolution is pretty good. It's every 4 days with the 2 Sentinel-2 satellites, for example. And the coverage is global. And actually, the data has been collected since 2015 with the same quality. So we can also do historical studies. But because the spectral resolution is bad, the methane signal is actually very noisy. So there's not enough spectral resolution to be sure some signal is methane. Could actually be something else. So that's the challenge with methane detection in multispectral satellite. And because the data is so noisy, so far methods that have been developed only enable to detect methane leaks that are about a ton per hour, and that's the 10–15% largest leaks in terms of total methane volume. And so what we did, we've been working on this idea for quite a few years. We developed an AI method to actually improve basically the signal-to-noise ratio and to automatically find the methane in this data. And what we end up with is with a method that can actually detect more than 85% of the leaks this time. So we're able to lower this detection threshold from about 2 to 1 ton per hour down to 200, 300 kilos per hour. And we can now actually detect most methane emissions at a global scale and completely automatically. And that's what the paper is about. So it describes the method to do so.
Thanks. This was already very extensive and touching on a lot of fields that I wanted to ask you about. So yeah, one thing I definitely would like to hear more about is the what you already mentioned, the AI method, or in your paper you call it deep learning. Can you, in simple words, because I know that's a very abstract topic, but can you tell us a little bit more about what actually is deep learning and what are you doing to your data? How do you treat or manipulate your data to extract this information that we haven't been able to extract before?
Yeah, good question. So AI in deep learning, so nowadays it's very much the same. So most AI methods are based on deep learning, and so it's a very vast topic. In our case, basically, the classical methods were relying on improving the methane signal and then having a human looking at it to determine if it's a plume or not. And this signal enhancement is basically, in some sense, something that works well for our eye. So it's basically just an image, and we look at it and decide whether it's a plume or not. One of the powers of deep learning is that it can look at many more dimensions than what we can look at. So when we look at a colored image, we're looking at 3 dimensions, basically. Typically images are RGB. So we're able to perceive and make sense of 3 dimensions. Deep learning can make sense of many more dimensions. And so in our case, with Sentinel-2 multispectral data, that's 12 dimensions. We actually improve the signal up to we combine those dimensions to have even more. And the deep learning model can make sense of it and have actually a much better capacity at detecting methane plumes than us that are limited to 3 dimensions. And so in general, deep learning, it's basically nothing more than fitting a function. So the way we're all used to it, so going down a gradient to find some minimum, except it does that in very high dimensions. And the whole field of deep learning basically was born from very smart tricks to do that very efficiently. So fitting a function that has millions of parameters very efficiently and lots of data that enables to find these correlations in high dimensions.
Thanks. And I wanted to ask you a little bit more about the methane leaks you were talking about before, and which you are now able to detect in the remote sensing data. Those methane leaks are very small point sources, and they only emit relatively small amounts of methane. So why is it still so important to monitor those, and what exactly causes those methane leaks in the petrol and oil industry?
Yeah, and that's also a very vast question. So to summarize, basically, so methane accounts for 20 to 30% of global warming to date, and its share in global warming is actually increasing because methane emissions are actually increasing for a few different reasons. One of which is that actually natural gas is becoming a more important part in the energy mix in many countries, including the US, including in Europe. And within those methane emissions, the oil and gas industry is about 30%. It's not only the oil and gas industry. Another main source is actually landfills. It's kind of a completely different source. And another big chunk of methane emissions is actually agriculture and dairy farming in particular. So cows, and that would be That's not really the topic of our study. So the topic of our study is to find strong point sources. So actually those point sources, even at a few hundred kilos per hour, because methane is 80 times more potent than CO2, 100 kilos methane leak is actually equivalent to 1 ton of CO2 per hour. And that's not a big leak in terms of that's a typical leak, I would say. So there's thousands and thousands of such leaks in the complex oil and gas infrastructure network, for example. Many landfills emit actually way more than that. So especially landfills that are not well regulated, they could be emitting tons per hour continuously, every day for years and years and years. And that's the equivalent of several transatlantic flights per hour. So those leaks are actually a very big source of global warming, and they're easy to address in some sense because they're point sources. Often it's some process that has a problem, and actually it's somewhat easy to solve. It could be actually a leak in some part of the industrial oil and gas network, which they would want to leak. I mean, if methane leaking is methane that's not solved, so everybody wins if it's fixed. So that's in some sense low-hanging fruit. If we can find those methane leaks, everybody has an interest in fixing them, and that would have an immediate effect on global warming.
Okay, sounds like it makes really sense to detect those methane leaks and their sources. So my final question would be about the implications of your work. Is your work, do you see it more like a monitoring tool to detect those leaks and to improve our understanding of global methane emissions? Or did you already look at the global methane emissions using this tool, and are we currently underestimating the global emissions, the amount of methane emissions?
Yeah, that's a very good question. So I will start by saying that first, it's a well-known problem that methane point sources are underestimated. It's not necessarily in bad faith. It's just that it's very hard to detect. It would require to constantly fly airplanes with high spectral cameras before to be sure to find every leak. And now we can approach the effectiveness of having planes constantly flying from this new method. And so we are finding lots of new leaks for sure, but that was expected basically every time. So NASA does this a lot. For example, every time there's an airplane campaign to systematically monitor oil and gas infrastructure, we find lots of new leaks because they're very hard to find. We know they're there. We know they're unaccounted for when we compare area-wide basin scale emissions with actually point sources. We see that we're missing 90% actually of the emissions. So we know they're there, and now potentially we have a new method to find them. So scientifically, it's interesting. From the point of view of climate change, it's also interesting from the point of view of the infrastructure, being able to find weak points in the infrastructure. Another strength of our method, because it's automatic, it doesn't really cost much to look at lots of data, including historical data. So Sentinel-2 that we're using, it's been orbiting since 2015 and 2016 for the two different satellites of the constellation, and so the data is the same since 2016, and so we'll also be able to look at historical data.
Okay, cool. Thanks. I think these were all the questions I had in mind. So thank you for walking us through your study.
Yeah, awesome. Yeah, my pleasure. Anytime.